Hi, everybody. Let's talk about how to find the center of mass for this lovely sign that I'm giving to my friend, Mr. Mazzoni. It's made of wood. It's got some lovely handwritten note on it. My goal is to find somewhere between the origin here, x equals 0, and this position B, somewhere along this line, if I can find the center of mass X component, then as long as I put the hole in my sign and hang a rope from it, I can be guaranteed that the center of mass will be below that point, and it's going to hang straight. So before I can give this to Mr. Mazzoni, I need to, the gift of math, of course, is what most people are looking for, obviously. So how do we do that? Well, the equation is the x-coordinate of the center of mass equals 1 over the mass times the integral of x dm. So we're only trying to find, relative to the x-axis here, we're only trying to find where along there the center of mass is located. We're ignoring the y component altogether, even though we could find that as well if we really cared. So we would be finding the centroid if we were doing that, but instead we're only going to find this. So our goal to find that x component is to relate the differential dm to x. So I feel like it would make some sense to think about what that means. So imagine I take a little slice of the sign right here, and then maybe right there's another one, and then way up here there's some other one. I want to think about those three slices. Each one is the same thickness. So each one of these has a dimension of dx thickness. Okay, this one too. They're all dx. But each one has a different y value. So the top of that little sliver, the height of it, varies. So this one over here on the far left has some pretty low y value. This one's kind of almost in the middle, and that one's a pretty big y value. So we need to consider how each of these different chunks of mass vary in terms of their area. So each one has the exact same dx, but they don't have the same dm. So how are we going to relate them? So let's leave that alone for a minute. Wait, let's use black. That's good. Let's think about the surface mass density. What does that mean? We generally use lowercase sigma to represent the surface density, whether it's mass or charge or something else. So we use sigma. And in this case, we're taking the quantity mass divided by the entire area. Well, the area of that triangle, so A, and let's make a note here. The area of the triangle is 1/2 the base, which is B, times the height, which is A. So we're going to remember this in case we need it. But what we need to think about is mass divided by area may be a constant. So that would make our differential element of mass dm. But what about the differential area for these three orange sort of chunks? Each one has the exact same thickness, but they have a different y value. So if we were going to write the area, that's no longer a triangle. That's a little tiny rectangle now. The rectangle's thickness is dx. The rectangle's height is y. So we would say that our area then is y times dx. That's the differential area. So for each little, what that means is, although each one may be a different height, since they have the same thickness, we're saying that there's a relationship between the ratio of the mass to y dx is going to be this constant sigma. Okay, so that makes it, now we have a way to relate the dx and the dm to one another. So let's draw a little arrow here. Sigma y dx then is equal to dm. Now we need to think about here, let's change colors. Let's use pink. Let's think about this line, this hypotenuse line right here. I want to think about what that must mean. In order to locate a particular y value based on the x value, that purple line has the equation y equals the slope times x. Well, the slope is the rise, A, over the run, B, times x. So we now have a way, we already found a way to relate dx and dm, but we need to get rid of that y in there. So that means that, and then we're going to keep this in a little box because I don't want to lose it. So that means sigma times A over B times x dx equals dm, or let's simplify this a little, A sigma over B x dx equals dm. That's not so bad. Now we can go back to our original definition. The location of the center of mass x component equals 1 over the mass times the integral of x dm. Well, x is, we're going to leave that alone, but dm is now a sigma b x dx. So now that we have x as our limits, we need to think about from what x to what x. So it's starting at the origin, x is equal to 0. And the largest extent of our sign in the x direction goes all the way to b. Remember, b is the base, a is the height. So I think we're ready to integrate it. Maybe we should simplify it a bit. So let's move all the things that are not related to x, all the constants, out. So that's a sigma over m times b times the integral from 0 to b of x squared dx. Yeah, that works. Well, the integral of x squared dx is 1/3 x cubed. So I've got this whole big expression, a sigma over mb. That's all still there. And now we've got a 1/3 that we need to think about. And we've got the function x cubed with our limits 0 to a. And this entire thing is the location of the center of mass x component, okay? So if we use our limit notation, the way, the typical way of applying the limit notation here is to plug in 0 to the function and subtract that away from whatever the number at the top is. So if we do that, we get a cubed. So that makes this, let's give ourselves some room here, x location of the center of mass equals a sigma over m b. There's a 3. I'm going to move the 3 right there because I'm lazy, times a cubed. Hang on, let's check that. A sigma 3mb times a cubed. That's not so bad. Oh, wait, my limits were wrong. I made a terrible mistake, and I am sorry for that. I apologize, everybody. Let's go back. This is from 0 to b. b is the extent. 0 to b, 0 to b. That's my fault. Which is good because I was about to get the wrong answer. So a sigma m b, all that's good. The 1/3 is still good. The only thing we needed to change was b cubed. Okay, that's not so bad. So how does that help us? Well, we can simplify a few things. Notice that one of the b's cancels, so now it's b squared. So that's a. And here's the thing. I need to group the a, the b squared, the 3 over m. I need to group them together because we need to revisit our original definition of sigma. Sigma was the total mass divided by the total area, which we said was 1/2 the base times the height, which is 1/2 a b times a. So that was the total mass divided by 1/2 the base times the height. So let's see how that helps us. Look, one of these b's cancels with another one of the b's. This a cancels with that a. The mass cancels out. And so we're left with a 1/2 in the denominator, which would become 2 in the numerator. We're left with a b, and we're left with a 3. So that becomes 2/3 b. So it turns out, if you are looking to hang a triangular sign for your good friend, Mr. Mazzoni, that what you want to do, let's pick a good color here to highlight this. How about blue? We'll go, so I'm going to estimate here. That's about 1/3, that's about 1/3, somewhere along this line. If you drill your hole right there and hang your rope, then your sign is going to hang correctly, and Mr. Mazzoni will be happy with you. So I hope you can replicate this process if you're ever faced with having to find the center of mass for a triangular shape.